Hello guys, welcome back to another lecture in this course. In this video, we shall be focusing into eigenvectors and eigenvalues. Eigenvectors are special vectors associated with the linear transformation that only change in scale, but not in the direction when the transformation is applied. Eigenvalue is a scalar or a scaling factor of the vectors. For example, if M is a matrix, is equals to a matrix, and V is equals to a vector, then we are saying now the eigenvectors of M, if only if M, V is equals to the scalar, which is lambda V, for scalar lambda. So we are using lambda as our scalar. So here we can see that the eigenvalue lambda is a scalar that when multiplied by an eigenvector simply scales up the eigenvector by the scalar. So the eigenvector is a vector that is not changed direction by the multiplication, but only in magnitude. Okay? Let us consider a matrix M, which is a two-dimensional matrix. Okay, this is the matrix that we are having. And the eigenvalues here of A, let us say are the eigenvalues, the eigenvalues. And remember, the eigenvalues, I said they are scalar or lambda. So the eigenvalues of let's say of M, the eigenvalue of our matrix are 3 and 1. So it means now the vector, the eigenvectors now. It means the eigenvectors corresponding to this to these eigenvalues are, let's say, eigenvector 1 is equals to 1 and 1, and the eigenvector 2, the vector 2, eigenvector 2 is minus 1 and 1. So if you are to check the solution for the corresponding eigenvectors that I will consider here, so if you are to calculate our matrix here, we say we use the formula MV1 for the vector, MV vector 1 and our scalar vector 1, as you can see. So it means we have to multiply here. We have to multiply. So we are saying our matrix 2, 1, 2, 1 and 1, 2, 1, 2 dot multiplying by V1. So V1 is 1, 1. So 1 and 1, which gives us equals to, let us multiply now. Row by column. 2 times 1 is 2, plus 2 times 1 times 1 is 1, so plus 1 here. 1 times 1 is 1, plus 2 times 1 plus 2, which gives us a total of 3. We can actually see that MV1 is equals to scalar or lambda V1, where our scalar or our lambda is equals to 3. Our lambda is equals to 3. And we have said that the lambda here, the eigenvalue is 3 for this matrix. The scalar is 3, and we have actually proved that the scalar is 3. So it means if we are to put 3 here, for example, let's say therefore, if you are to say 3 times V1 for our lambda, where V1 is 1 and 1, we are saying 3 by 1 and 1. It means that we are going to get 3. So here we are saying V1 is equals to 3 all over 3, which gives us back 1 and 1. And same applies if we are to do V2 for the eigenvalues and eigenvectors that we are given. we can say for mv2 is equals to our scalar or lambda, v2 is equals to our matrix, which is 2 and 1 and 1 and 2, and dot our v2 is minus 1 and 1. So here we can actually see 2 times here it's minus 2 plus 1 and minus 1 plus 2, which gives us a total of minus 1 and 1. And it means that our lambda this time is equals to 1, where this is scalar minus 1 and 1. If you are to divide by 1, we still get v2, and v2 is minus 1 and 1. Sometimes the eigenvalues are not given, this scalar, the ratio or the lambda. It is not given because in this example, I just give you an example after I give you all. Let us say if they are not given. If they are not given, it means we have to use the formula of determinant of A minus our lambda and identity here equals to 0. And here we are just saying where A is our matrix. And here also I. This is letter I, not 1. I is our identity matrix. So if you are not given the lambda, this scalar here, it means that we have to apply this formula. For example, and also I think we know identity matrix, we are talking about 1, 0, 0, 1 if it is in 2 dimensions. But if it is in 3-dimensional matrix, we are saying 1, 0, 0, 0, 1, 0, and also 0, 0, 1. Same applies in 4 dimensions, 5, and on and on and on. But here in 3 dimensions, this is in 2 dimensions in this one. Let us take a look into a 2x2 matrix or a 2-dimensional matrix where we are not given, and let us use this example. Let us use this example 2, 1 and 1, 2. Assuming we are not given this lambda or the eigenvalues, we are not given the eigenvalues, which is 1 and 3. Let us find ourselves the eigenvalues. So assuming we are not given, and our matrix, it is still our original matrix, which is 1, which is 2 and 1, 1 and 2. And assuming we know that our eigenvalues that we are having is 1 and 3. Now we need to find, we are not given, we need to find the eigenvalues ourselves. So what we do, we write our formula down. This is our matrix. So we say determinant is equals to A minus lambda and identity, which is equals to A for our matrix, which is 2, 1, 1 and 2. Now we have our matrix minus our lambda, which is going to represent our scalar, the two values that we are looking for that you are not given, identity matrix. So you check this matrix. If this matrix is a 2x2 matrix, you write the identity matrix of a 2x2 matrix here. If this matrix is a 3x3, you write the identity matrix of a 3x3 matrix. So it is simple, right? If we are here now, it means we are going to multiply first. Let's say we are having 2, 1, 1 and 2, it will retain as it is, minus. So you multiply our scalar with everything inside. So this times this, you get our lambda here. Here we get 0. Here multiply, we get 0. Here we multiply, we get lambda. So we are having lambda 0, 0 lambda. So it's like an identity of lambda. So then now, what we can do now, we have to perform matrix operation. So taking the determinant to find the eigenvalues, especially for our polynomial, obviously here it is all equals to 0. Because we say the determinant here, it has to form an equation which is equals to 0 in our polynomial. So to find the characteristics of polynomial A or the matrix, what we can do now, we can add 2 minus this. We just do the way we do matrix operation of vectors is the same. 2 minus lambda, we get 2 minus lambda here. 1 minus 0, it means we get 1. 1 minus 0, we get 1. 2 minus lambda, we get 2 minus lambda here, which gives us equals to 0. What we need to do now is to find the determinant. And when we are looking for a determinant, assuming it's 0, 1, 0, 1. To find the determinant of this, we say 1 times 1. Multiply this and this, minus this times this, so minus 0 times 0. I think you get the concept. So now we are multiplying 2 minus lambda, bracket 2 minus lambda, then minus, since we are looking for the determinant, minus 1 times 1, all equal to 0. So now let us do our expansion here. 2 times 2, we get 4. 2 times minus lambda, we get minus 2 lambda. Minus lambda times 2 is minus 2 lambda. Minus lambda times minus lambda, we get a plus lambda square, minus 1. As you can see here, all equals to 0. So 4 here minus 1, we get 3. Minus 2 lambda minus 2 lambda, we get minus 4 lambda, plus lambda square equals to 0. And if you are to look into this one, we can see that we are having a quadratic equation, ax squared plus bx plus c equals to 0. This is a simple quadratic equation that you can see. And when you are having a quadratic equation, we have several ways of solving quadratic equation. We can use a general formula, x is equals to minus b plus or minus square root of b squared minus 4ac all over 2a. This is just a general formula. Or we can use it by splitting the middle term, or meaning factorization concept. We can use factorization concept, or we can use completing the square. So let us use a simple way. Let us use splitting the middle term for factorization. So if you are using splitting the middle term, if you multiply these two, it means we have 3 lambda squared. So we have to find two numbers. When we multiply, we get 3 lambda squared. If we add or subtract those two numbers, we get the middle term, this middle term. That's why we're calling it splitting the middle term. So minus 3 lambda times minus 3 lambda dot the minus lambda is equals to 3 lambda squared. Minus 3 lambda, let's say plus a minus lambda, we get minus 4 lambda. So we are going to split this middle term with the minus 3 and minus 1 here. So let us go here and say 3 minus, instead of writing minus 4 here, we are writing minus 3 lambda minus lambda plus lambda squared. Because minus 3 lambda minus lambda, it gives us minus 4 lambda. If you multiply these two, you get 3 lambda squared, all equals to 0. So this is the polynomial that we are having. Now, what we can do now is factorizing. Here, let us factor out 3. 1 minus lambda here. And let us factor out minus lambda, our scalar. We get 1 minus lambda here. Because we are saying this into this, I think you are following. Now all equals to 0. So our final answer here, we are getting 3 and minus lambda and 1 minus lambda. So we have to form now two equations, or we are setting our polynomial equation to 0, as you can see here. 3 minus lambda is equals to 0, or 1 minus lambda is equals to 0. So minus lambda is equals to minus 3. If 2 minus lambda is equals to minus 1. Then we divide both sides by a negative 1. Cancel the negatives here. It means lambda is equals to 3. And also same applies if we divide both by a negative 1, we cancel this and we cancel this. It means our lambda also is equals to negative 1. So here we can see that the eigenvalues of m are lambda equals to 3, and lambda equals to 1. As I already put in place here on top, as you can see here, I've mentioned that even though on this question that we did above as an example, I said eigenvalues lambda are 3 and 1, and we did a solution to find the vector 1 and vector 2 and see how we can, and after finding all those vector 1 and vector 2, I said, what if you are not given the eigenvalues? How are you going to solve so that you find those eigenvalues? We use the determinant, which is a minus lambda identity equal to 0. So assuming that we know that yes, the lambdas are 1 and 3, let us try to find using the same matrix here. So as you can see, I demonstrated that our eigenvalues, the eigenvalues of our matrix M are lambda, 3 and 1. These are our eigenvalues. You can see now that to find the eigenvectors, if you are to find the eigenvectors, it means you are just saying your matrix times the vector is equals to the lambda times also the vector that you are looking for, or mv equals to our lambda v. If you are looking now for eigenvectors, you'll be now just substituting the values. And we shall be looking into how to find the eigenvectors when we are solving for singular value decomposition on our next video. I think for now, let me just demonstrate a little bit on, for example, when you are using Python, how you can use Python to solve for eigenvalues and the eigenvectors. Given a matrix, and this matrix is a two-dimensional matrix with the 2 and 1 and 1 and 2. These are our values. So we need to calculate our eigenvalues and the eigenvectors. So we create our variables here, and this we have imported our linear algebra dot. We are saying we need our eigenvalue in this matrix. Okay. So by running this line of code, we can actually see now our eigenvalues, and these are the eigenvalues that we have solved here in our solution, which were 3 and 1. And also in Python, we can actually see that Python also managed to display that. Now, I want you also to find the eigenvectors. I want you to see how we can find the eigenvectors. I think this is your homework. Thank you for watching. See you on the next lesson. Bye-bye.